Right, now the next experiment that we do is current voltage characteristics. So I always write current voltage characteristics like that. I for current, V for voltage, or current potential difference characteristics. Now we do the same thing again in that we have a test circuit, and in this test circuit this time I'm just going to draw it in a slightly different way. I'm going to put the ammeter on the other side just to show it makes no difference whatsoever. And this time we've got one of these variable resistors in the circuit. Now if you remember what I said before, this part here just represented a power pack, and the variable resistor was a method of altering things in the circuit. It was altering the amount of output of the circuit. So this is just a fixed resistor, and what we do in this experiment is we change the value of this resistor, and by sliding it up and down, and what that does is it changes the amount of electricity that goes through the circuit, and then we measure the current and voltage. Now it's easier if when we're taking the results, if we write the potential difference there, volt, and the current there. Current amps, sorry, there you go. Current amps. Right, now what we'll get with this is we'll get a graph of the thing, the first thing that we do, which is the potential difference there, and the current there. Now, we normally write this I tend to be a bit lazy sometimes, and I'll just write IV like that. Now, these IV characteristics, because it's a fixed resistor, what you expect to get is a straight line. Now, let's just pick a slightly different resistor. So let's say we picked a resistor which had a bigger resistance. What would we expect it to look like? Now, if we get something with a bigger resistance, we'd expect it to maybe look like that, because it'd make more sense, except, let's have a think about it. So we said that the number of volts was the electrical push. So a number of volts was the electrical push, and then we said the current was the flow. So if we had something which was maybe a higher resistance, then we would expect to get less flow with the same push. So when I say less flow with the same push, less flow, less current with the same push, the voltage. So we might expect, so that's a bigger resistance and that's a smaller resistance. Right, but notice it stays the same, as in it stays the same gradient. Notice it's a constant straight line, as it were. Now we sometimes draw this in a slightly different way, in that we draw it IV like that, where we've got these negative regions. So this is like negative voltage, this is like negative current. And what negative means in terms of physics and circuits, it means it's going backwards. So we see what happens when it goes backwards in the circuit, and we end up with a straight line again, which goes, so basically this region here means that it does exactly the same backwards. So if we swap around this battery there, swap the terminals around, wire it up the wrong way, it doesn't matter, it still does exactly the same backwards. Okay, now the reason we point that out is because one of these examples doesn't. So when we do this circuit, we start off with a very, very high resistance on there, and so it's not got a very big output. So this might be 0, 0, and then it might go to 1 volt and 2 amps and 2 volts, 4 amps, 3 and 6, and it keeps going like that. And we change this as we go along, and we generate a set of results. So this is going to be not much electricity going through it, and this is going to be lots of electricity. And so that's what we're doing. We're changing the output of this power pack, and we're seeing what it does when there's a little bit of voltage and current or a lot of voltage and current. Okay, right. Now I'm going to draw these in 3 ways now. So first of all, we repeat this experiment 3 times. Now the first experiment that we do looks like this, and it's got a fixed resistor in there. Now, I'm not going to bother drawing the variable resistor anymore. So this is our test circuit. Now let's say I want to put that test circuit, and instead of looking at a fixed resistor, we're going to look at something else. I'm going to look at a bulb, and we're going to see what happens. We're going to do exactly the same experiment, but this time with a bulb. And then thirdly, we're going to do exactly the same experiment again, but with this device, which is a diode. So there's the 3 test circuits with the 3 things in. So we've got a fixed resistor, we've got a bulb, or sometimes called a filament lamp, and a diode. Okay, so fixed resistor, bulb, diode. Right, now if I was going to draw the results out for these, if you remember, the results for that one was a straight line. Now, the result for this one will be a curve. The result for the third one goes across for a while and then shoots up. So you get nothing, 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 and then it shoots up. Now, it gets a bit more interesting, and these are the ones we need to remember when we consider the negative and positive voltage and current as well. So that was current, voltage, current, voltage. And these are some shapes that you need to remember. You also need to know why it does it. So fixed resistor, straight line. Bulb is a curve, and it goes like that. Now notice how it never quite flattens out at the top. It always just kind of gets less steep and less steep and less steep, but it never flattens out. And the third one, this goes 0, 0, 0, 0, 0, shoot up like that. Okay. So we've got fixed resistor, got bulb, filament lamp, and diode. Now the reason why these happen, first of all, is if you think about the equation R equals V over I. R equals V over I, so it's like this divided by that. If in a fixed resistor, the resistance never changes, which means that that gradient never changes. Never changes. Okay, which means it's always a straight line. So that means that this gradient kind of represents the resistance in a way. It's actually the opposite way around, because the steeper the line is, the less the resistance is. But this, so what this represents when we're talking about a bulb is, notice that the steepness starts to change. And because the steepness changes, that means the resistance changes. Now, with a bulb, inside a bulb is a tiny bit of wire, and that wire gets really, really hot. And as those atoms in the wire are getting really hot, those electrons are trying to get through the wire. Here they are, these little electrons, and they're trying to get through. Except these things are vibrating around like crazy because it's hot, and they're vibrating around like mad. And as they're vibrating around, that makes it more and more difficult for the electricity to get through. And as the electricity, it's more difficult for the electricity to get through. So that means the resistance increases. So the higher the current and voltage, the brighter the bulb, the hotter the wire inside, and the higher the resistance of that bulb. Okay, and that's exactly the same, identical backwards. So just backwards is exactly the same. Now this is an interesting one, and this is the reason why we do the negative graphs in the first place. So just to remind you, this is a diode. Now what a diode does is it only lets electricity pass through in one direction. And a diode also needs a tiny bit of current first, a tiny bit of electrical push first, in order to allow the current to flow. So it needs a tiny bit of potential difference in order for that current to flow. So here we are, and backwards, if you notice, there is zero current. So that means it doesn't allow the electricity to go backwards. It only allows the electricity to go forwards, and it needs a very, very small potential difference, and then it lets the whole thing. So the current can only flow one way, and it needs this tiny little amount there of voltage before it'll let any current flow through. Okay, so that was current voltage characteristics.